Yeah, it's a great pleasure to be here finally after all the slow-moving traffic. So I'm Leo. I'm a research scientist working at Adobe Research. So I work in information visualization and visual analytics. And the work that I'm going to talk about today is in collaboration with Jeff Hare, who was at Stanford and recently moved to University of Washington. So I worked as a postdoc with him. Together we were looking at the problem of addressing interactive latency in big data visualization. So I think latency is really a central topic in many areas of computer science, ranging from hardware to networking to databases and interactive visualization systems. And when I was making the slides earlier today, I didn't realize that I was going to be stuck in the traffic, and yeah, and it's truly a frustrating experience. I guess people just don't really have a high tolerance for delays and high latency. So basically, that means that we have really two important questions to ask. The first one is how do we reduce interactive latency in big data visualization? And secondly, it's more a question about human behavior. Is that how do we get a clear understanding of how interactive latency affects people's behavior in visual analysis? So I'm going to start by talking about research that addresses the first question. There are actually quite a number of different approaches we can use to reduce interactive latency in data visualizations. The simple thing is try just to get more memories and fit all the data in memory. And so, for example, systems like Tableau actually use an in-memory data store and basically do data transformation and queries in memory. And also other works like, for example, Nanocube takes a step further, tries to do something clever indexing to speed up the query process. And also, since we have more, since the hardware is getting cheaper and cheaper, we can do querying and processing on multiple machines or parallel processors like GPUs. So these approaches inspire us to come up with the idea of in the system immense. But here we're taking a more holistic approach. So we start by thinking how we actually scale the visualization perceptually for the users. And from the visual design, we think about how we can apply computational techniques to address the issue of interactive scalability. Right. So first of all, to think about how we can actually address the problem of perceptual scalability, we choose to use binned aggregation as our primary data reduction strategy. The guiding principle is basically that we believe perceptual and interactive scalability should be limited by the chosen resolution of the visualized data, not to the number of data records. So here's what I mean. So here we have a very simple scatter plot of about 10,000 data points. As you can see, there's a problem of overplotting here. So what we can do about this? One technique we can use is called alpha blending. It's basically try to assign transparency values to each data point, so that like denser areas will have a will basically have a higher value for the transparency. But this technique still requires us to actually plot every single data point, which will not be very scalable. So there are other approaches. So for example, we can just do a small subset of the sample by the data by using sampling, or we can do some computational statistical modeling just to give a kind of outline of the data set. Or we can actually apply binned aggregation. So the idea is that we divide the x and y axes into intervals, and then we count the number of data points falling into each of the bins, and then we color code the density by color. So these are the different approaches we can use to actually visualize real-world data sets. So to experiment with these, we took a data set, that's a public data set that's about 4 million user check-ins on the service BrightKite, which was similar to Foursquare. And so using Google Fusion tables, which applies stratified sampling to the data, we get this visualization. Clearly, each dot here is only one user checking. And so we're only seeing a very small percentage of the entire data set here. So from this visualization, you can sort of see, OK, people are checking mostly from big cities, which is kind of expected. But you can also notice that there's no checking in Mexico, there's very little checking from Canada. Is this because the data simply isn't there, or is it because it's just missed by the sampling process? We don't really know. So instead, we're thinking about binned aggregation as an alternative approach. So this is what we can see using binned aggregation, and we get a more complete picture. So here, the red spots are basically dense areas with lots of check-ins. And we can both see the entire overview and also some very specific outliers. So for example, people actually made up an account reporting the locations of the hurricane paths. That's the long line, yeah, that you see across the Gulf. So obviously, in this case here, binned aggregation is actually a better choice. Right. So applying binned aggregation to different types of data, we actually get different types of visualizations. So for one-dimensional data, we get, for numeric data, we get a histogram. And for ordinal or categorical data, we get a bar chart. And for temporal data, it's a line graph. And for geographic data, we actually have a choropleth map. And for 2D, two-dimensional plots, these are different variants of the heat map. So the geographic visualization was actually a heat map overlaid on top of a map. All right. So having decided that we are going to apply binned aggregation as our primary data reduction strategy, we use two techniques here to ensure real-time interaction with the data. The first is called multivariate data tiles, and the second one is we try to do parallel query processing and rendering on the GPU. So before I go on to explain how this works, I'm going to show a quick demo of the system. All right. So I have, let me refresh this. I have here the 4.5 million user check-ins that I just described, visualized in 5 visualizations, a geographic heat map, and then 3 histograms showing the distributions of check-ins by month, day, and hour. And also, we have the top 30 user check-ins, basically broken down by individual users. And so when you mouse over the visualizations, you get a very interactive experience. So this is a technique called brushing and linking. When you select a value in the day, for example, you can see how the data actually is correlated in other views. And so again, from the overview here, we notice, OK, there is this long trail of check-ins. So we can try to zoom in to see what happens. OK, let me pan it. All right, so this is the hurricane path. And to get more specific information, for example, I can brush over the month histogram. And it seems that this is only happening in September. And if I mouse over the days, you can see the hurricane is actually coming in and then landing in Texas over the course of about 10 days. So this is the kind of interactive experience you can get when you are trying to visualize data using immense. All right, let me go back and explain how this works. So to visualize the data set, we first pre-compute multivariate data tiles. So these are projections which corresponds to materialized database views. So these projections provide data for dynamic visualization, and they're much faster than a traditional Datacube in memory. So for example, here we have like 4 visualizations, a geoheat map, and 3 histograms.
What do you mean by projections? Can you describe a little bit?
I'll explain that in the next few slides. Yeah, so let's say we want to visualize these 4 visualizations and link them together like what I did just now using brushing and linking. So a naive approach would be to compute a full-size data cube. So we have 5 dimensions here involved in the visualizations, the month, day, and hour, and also the X and Y dimensions for the geographic heat map. So this is a 5-dimension cube, and suppose we divide this up into each of these dimensions into bins. We have a total about 2.3 billion cells to compute. And then to do brushing linking, so for example, when a user mouse over January, we need to actually select all the cells that matches this selected value, which is about 200 million cells. And then we need to do a sum up along the day. So that gives us about 6 million cells. And then we do another sum up along the hour dimension. So here now we have a 512 by 512 matrix we can use to plot the geographic heat map. But obviously, this approach is it's not very efficient because the Datacube often is too big to fit into main memory, and also it's also too slow to query. So one idea we had is to decompose this full Datacube into smaller ones. Because we're only dealing with 1 or 2 dimensional plots here, so for any pair of this 1 or 2D bin plots, the maximum number of dimensions we need to support brushing and linking is only 4. So in this way, we can break down the 5D cube into multiple 3D cubes, as shown here. But this alone is not enough, because imagine here you have the zooming operation. So when you zoom in, potentially the geo heat map will have thousands or even millions or billions of bins. So to query over that is still very inefficient. So we are inspired by the idea of tiles, which are commonly seen in services like Google Maps. So the idea is that basically we segment bin ranges to form data tiles, similar to the idea of map tiles. So here, for example, for the x dimension, we break them down into 2 ranges. For the y dimension, we also break it down into 2 ranges. And for the day, since it only has 31 bins, we just don't have to worry about it too much. So the process of basically going from data cube to data tiles is something like this. Just chopping it up into smaller cubes. As a result, to actually support brushing and linking between these 4 views, all we need is 13 data tiles. So first is the x1, y1 dimension with each of the temporal dimensions, and then x1, y2 with each of the temporal dimensions, x2, y1, and x2, y2. And finally, to enable brushing and linking between the temporal dimensions, we need an additional data tile. So altogether, we have 13 data tiles. And the reduction is pretty dramatic. So we actually go from about 2 billion bins to about 17 million bins. And if we apply compression techniques, we can actually get all the 13 data tiles in about 350 kilobytes, which can be easily transferred over the network. So based on this idea of data tile, we designed the architecture of the immense system. At the server side, we assume that data is stored in like a database like a SciDB or Postgres, and then we can pre-compute a bunch of data tiles. And when a user specifies through the UI control that he wants to see some certain visualizations, the client intelligently fetches some relevant data tile to the client side and render the visualization. And when a user does brushing and linking, the processing is done purely locally on the client by querying the data tiles stored at the client. And then for zooming and panning, the client will actually contact the server again to fetch additional relevant data tiles. So just purely on the client-side processing, we actually basically pack each of these data tiles as an image because it's easy to bind them as textures to the GPU context. And then we first pass them through a query fragment shader program to compute the roll-up results, and then store them on the image on the off-screen frame buffer object. And then from there, we do another second pass and render it on the screen on the canvas. Right. So we did some benchmarks on this approach. We simulated brushing and linking across plots in the scatterplot matrix. We compared immense versus the full Datacube in-memory approach. We generated about 60 synthesized data sets by varying 3 parameters: the bin count per dimension, the number of records, and the number of dimensions. So here's the result. This is the result for the full Datacube. And the vertical axis is the frame per second, and the horizontal axis is the data size. So we tested from 10K data points to 1 billion data points. So are we actually supporting this kind of right pace of analysis? So that leads to the second question, which is about how does interactive latency affect user behavior? It turns out there are some works in CogSci and HCI literature which addresses this problem. So Newell, who is a very famous cognitive scientist, he proposed this theory of unified theories of cognition. And he proposed a framework that addresses the time constants that are happening at each levels of human cognition. And similarly for HCI researchers like Stuckart, who proposed similar frameworks. And they're often emphasizing that human action can take as little as 100 milliseconds to actually complete a low-level task. And some other people actually disagree. So for example, so this is a very famous paper where people are trying to understand how people actually try to use the environment, the objects in the environment to basically bind to their cognitive programs for really fast processing. And the thing they're calling is something called Deictic Strategy. So in this 300 millisecond interval, people are actually reorienting their bodies or heads to actually bind objects in the world for task performance. And what they find out is that very small changes in the cost of binding can cause really drastic cognitive differences in cognitive behavior. And there are a number of different studies which actually confirms that. So in different application domains, we actually, a small change in latency can affect how people actually approach the problem completely. So a natural question is then, does this apply for the domain of visualization and visual analysis? So to do this, we use the immense system to set up a study where in the base, we have all the baseline conditions. And then we added only half a second delay for each of the unit operations in the immense system. And then we applied this to two different data sets. The first one is the 4 million user check-ins you have seen. And then the second one is about 140 million flight records information. And we ran a study with 16 participants. We got 32 observations. And we recorded everything that user did with the visualizations. And also we asked them to think aloud, to report the findings they have. And then we transcribed all the ready recordings into some scripts. So for the log events, we captured both the system events, which are the zooming, panning, selection, brushing, linking, and so on, and also the mouse events like mouse down, mouse up, mouse move. And for the system events, actually, we actually keep two types of system events. One is the events that are actually triggered by the users. And the second type is what we call processed. So these are the events that are actually captured and processed by the system. So a preliminary analysis shows that, indeed, users actually perform differently, just with this half a second difference in interactive latency. So people tend to query more and interact more with the systems. And then we're also very interested in the qualitative aspects of this study. So how do we actually evaluate how people are doing? Because we all know that the purpose of visualization is insight, not pictures. So actually, I'm in the middle of the process of trying to counting all the insights that people generated from the system. And there are some interesting things just to think about. So what is an insight? For example, one person reported that, okay, many new airlines emerged around the year 2003. And another one reported these in like as many concrete examples. And the third one reported something similar, but also with some additional information on the different aspect of the data. So we're in the process of trying to come up with the right categorizations that capture this, all these diverse insights that people are reporting. Yeah, just to sum up, so to address these two questions, the first one, we designed and implemented a system called Immense that tries to support real-time interaction with big data. And to answer the second question, we're doing some work in progress that try to understand user behavior from a quantitative and a qualitative analysis. All right. So with that, I'd like to thank my collaborators, Jeff here and Bia Zhang, and I'll be glad to take questions. Thank you.
So how much different those actions were? What actually happened when you reduced delay?
So we're just doing some statistical testing, and we find there is a significant difference in terms of brushing action, especially. With only like half a second delay, people brush much less. Yeah.
Did you try different time intervals, like half a second, quarter second, seconds?
We would love to do that, but I think it's very hard because for each condition, we will need to ask the participants to do like a 30-minute study. So that's a lot of work on us. Yeah.
How did you come up with half a second?
So we actually initially tried 1 second, which we think is kind of reasonable because many of the database systems they argue that like 1 or 2 second delay is reasonable to run a query. But actually, just with 1 second delay, people are thinking the system is not really usable anymore. So we reduced it to half a second.
Actually, there are studies which show 200 milliseconds. Like on a website, people leave more often if the delay is more than 200 milliseconds.
Yeah, that's right. I think there's a study maybe from Google. Yeah. Yeah.
Can you give an example or two of? Can you give an example or two of what insights can you draw from Foursquare Chicken's data, or users may possibly the interpreting visualization overlaid over map can be I don't know, like it may not be of any value at all.
It depends. I think partly it depends on the data. Sometimes maybe just the data itself is not that interesting. But I think it's useful just to get an overview on the map. But definitely there are other dimensions we can look at. Yeah.
So your data tile method can it be applied to other types of visualization? Instead of the geo visualization?
I think so. That's what I tried to explain in this slide. Let me go back here. This data tile method applies to all the basically multi-dimensional data. So as long as your data is in a data table, you can apply it. And then, so for different types of data, so you can get different types of visualizations. But behind all these visualizations, the data tile method still applies.
Okay, thank you so much. Let's thank again our three speakers for today.
Thank you.